Good morning, ladies and gentlemen, and many thanks for the kind introduction. And please do not tell my superiors that I'm here today because we have our wonderful Aachen colloquium at the same time today. So, okay, Squaring the Circle is the title of my presentation, and please apologize, fasten your seatbelt if I eventually be a little bit fast in going through my slides because I have a lot of material with me, so hopefully I can meet the timeline. I have structured my presentation into these 5 sectors. So first starting with some market situation, drivers and challenges. I think we have heard already a lot of that in the previous speeches. Then talking about the key aspect, which is the emission compliance, stepping over to overall machine efficiency and measures to improve it. Then stepping into carbon neutrality, which is a main driver for the upcoming future. And then I close my speech with some summary and conclusions. Starting on the first point, so looking a little bit on some analysis done in, I guess, the Netherlands, showing the real-world emission behavior of different kinds of non-road mobile machineries. And as you might remember, around about 10 years ago, we had a certain incident here in Europe, which in a certain way, speaking it in a neutral way, reminds me of that. The intention of the engaged emission legislation, stage 5 in Europe, is not met in a way like the regulators would like to be. We have in all-day real-world operation, we have smaller or larger deviations from the overall expected emission performance, and I can only, we from FEV perspective, can only encourage all the OEMs to take care of this real-world emission behavior in order to lower the pressure which could build up in that region by non-governmental organizations, green parties, and whatever. And I think we have learned about that already before in the previous speech. For sure, we know that this is in a certain way already known, and we are working on upcoming new emission legislations. Europe is a little bit behind. China is maybe a little bit closer, but for sure, US is currently setting with the Tier 5 final standards a certain benchmark in the upcoming emission regulation. You see here the main numbers for the currently discussed Tier 5 stage. Finally, you see some note in there that I think due to the new administration, for the first time included simultaneous CO2 reduction aspect of around about 6 to 8% for the new regulation. I think due to the new administration, it will not be continued and will be eliminated from the final definition of the Tier 5 standards as function of time according to our, let's say, local intelligence, which we have in the US market. You can reach these numbers in different approaches. You can either follow the stepwise approach by combining the options 1 to 3, or you can go the way via option 4 by more or less using the time as maximum to sell Tier 4 final standards and then move your entire portfolio directly to the Tier 5 final standards. There are some delayed deadlines existing for the small volume manufacturers, which have a little bit more time to meet the emission regulation. But in principle, and according to our knowledge, most of the OEMs which we are cooperating with, they are following the approach to directly achieve the Tier 5 final standards, because the rather limited time for the interim phase is not really paying off because you have to develop too many different variants and solutions. So it is under the bottom line not really attractive, at least for the majority. A further look on the numbers which we have to achieve as it is currently discussed. So I think it is clear the main focus is given on NOx emissions and particulate emissions on the main cycle, which is the NRTC and the NRSC. There is also some aspect of the non-methane hydrocarbons. And as I said before, the CO2 is in the current proposal still included, but I would not put too much focus at the moment on this, as we expect that it will be eliminated. Besides the standard cycle, there's the introduction of a new cycle, which is the low-load cycle standards, which is defining another significant challenge for the solution, because it is covering a real or quite frequent real-world operational status of the machine, being in idle conditions for a rather long time on the construction site or on the agricultural field. So I think this is, in summary, a significant challenge to find the optimal technical solution. But we should not forget that the overall Tier 5 standards consist of multiple requirements, not only on the tailpipe emissions, not only on the CO2 emissions. There's an increased useful life incorporated. There is this additional test cycle. There is in-use testing, which is expanded. There is OBD and OBMD included. There are some SCR inducements formulated. So there's a lot of regulatory framework around the overall emission standard. Nevertheless, I think we can summarize and compress the requirements on two key challenges. The first one is more or less described by the main test, by the NRTC and NRSC cycle, where we have to achieve a reduction of 90% of NOx emissions and 75% on the particulate matter, which is especially for the cold NRTC cycle a significant challenge. And on the other hand, the second key challenge is the new supplementary test cycle with the low load conditions, where we have the massive challenge to meet adequate conversion efficiencies in the after treatment systems in order to pass the thresholds. And all of these, for all of these challenges, the solutions have for sure to be developed under quite tight boundaries regarding costs, package, complexity, robustness, and I think all of the OEMs are also trying to identify a kind of unique selling point for their products in order to differentiate from the competition. This is more or less a driver coming from the overall national or market-wide regulation. Besides this, what we see also taking place in Europe very much is local limitations and regulations, especially in bigger cities, urban hotspots, where the local government is introducing legislation regarding zero-emission construction sites. You see it here on this chart, very much pronounced in the northern countries, the rich countries, Denmark, Norway, Sweden, but also the UK, quite prominent here, and also in the Austrian and Switzerland region. We have this tendency by a certain time in the near future that inside of these urban hotspots, fossil-free construction activities or zero-emission activities have to be achieved and safeguarded. What are the solutions for that? I think we have the classical separation here between the smaller machinery and the larger machinery. I think for the smaller ones below 56 kilowatt, there's a massive focus on the internal optimization of the combustion process in order to reduce the engine out emissions. For sure, we have to use a particulate filter in order to manage the challenging PM limits. For one or the other application, maybe an external hydrocarbon injector may be needed in order to ensure a proper regeneration. For the larger and more powerful machinery, I think we have to realize the solution on the combination of internal measures with quite sophisticated exhaust after treatment systems. However, from our perspective, there's not a clear mandatory need for a twin dosing SCR system. For sure, it is a very powerful exhaust after treatment system which allows a very high flexibility, especially if we also talk about the extended useful lifetime which we have to safeguard. But according to our latest activities, it is not a clear must. We also see a chance to meet this with a more cost-effective exhaust after treatment system based on an upgraded stage 5 emission solution. So, stepping a little bit deeper into this emission requirement for the upcoming future. So, as I said, we have two main key challenges, and we have identified 4 major areas for activities in order to meet these legal requirements, focusing on the Tier 5 final standards, which are currently published for the future. So overall, we think that the introduction of a combustion mode coordinator in order to optimize the combustion boundaries for all of the different operational conditions is a quite helpful and good measure. And then we have for the key challenge number 1, which is the NRTC, NRSC cycle area. We have to work on the right sizing of the engine, on the right displacement. For example, avoiding eventually higher power densities than 30 kilowatt per liter, or respectively avoiding twin turbo, because it's a massive burden for the exhaust after treatment system. If here this massive piece of metal is between the engine outlet and the exhaust after treatment system. Then for sure, one major part is the optimized combustion system with some kind of cooled EGR, maybe switchable cooled EGR for consideration of the cold NRTC cycle. Then some enhanced and upsized EATS system, and for sure also some new control logics in order to maximize the usage of the potential of the hardware components which are installed on the engine. For the second part, for the key challenge number 2, for sure also the optimization of the combustion system is essential, because probably we cannot rely massively on the exhaust after treatment system, because we will always be on a rather low level of temperature in the exhaust line. For sure we have to consider, if the CO2 reduction will not take place, we have a degree of freedom in order to work with some heating strategies. If the CO2 reduction will maintain in the legislation for Tier 5 final, this for sure makes a big burden on some aggressive heating strategies, and we have to compensate this with overall reduced engine efficiency in order to meet the legal requirements. And then for sure also here we need the upgraded EATS for the low load cycle, and also some new control logics. So we have conducted a certain kind of analysis, deep dive analysis, for meeting this for above 56 kilowatt engine class. So the first example here is coming from the more or less the main part, which is the NRTC related portion, where we have to consider the cold and the hot cycle. So starting from some certified engines which are delivering 80 milligram per kilowatt hour in the current Tier 4 final status, we see here for the NRTC portion of the emission regulation, we see the major part coming from some torque curve reshaping, the introduction of a more flexible and powerful boosting system with a VGT turbocharger and some corresponding recalibration, plus the utilization of hot EGR in order to uplift the temperature level. The combustion system itself and also the exhaust after treatment system probably have only a minor portion, and this leads us finally in our walk here to the target for a D-green system, which is here showed with 10 milligram per kilowatt hour, which is the legal target of 40 milligram per kilowatt hour minus a safety margin for the production scattering of around about 25%, and another margin for the aging over the extended useful lifetime, so that the engineering target is somewhere in the region of 10, 12, whatever milligram per kilowatt hour, which currently should be focused on. If we continue, then the next one is the NRSC cycle, so the steady state cycle, and here we see how the picture changes significantly. So here we have only a minor portion because we are for sure at very hot and stable steady state conditions. Here's only a minor portion of the overall result coming from the torque curve reshaping, VGT and hot EGR stuff. Here the main focus is coming from the exhaust after treatment system in order to meet the requirements under the steady state conditions, which is changing once again if we go to the low load cycle. So here we have once again a very big focus on the measures like torque curve reshaping and hot EGR in combination in order to meet the target, and once again the basic combustion system and the exhaust after treatment system are probably only delivering here a roughly limited share of the overall achievement. In addition, for sure, just for completeness, if we have to meet the CO2 emissions, besides this, also here we have major areas which contribute to the overall result. Here for sure, in terms of efficiency, the combustion system is one of the main aspects in order to meet that, if this is required from the legislation. Otherwise, for sure, friction improvement is another part of efficiency optimization. But here we have to see how the final emission standard will be formulated when it is introduced into the market. So looking into the different areas, that's just summarizing them. So for sure, the base for the future will be an enhanced low NOx combustion system, considering displacement right sizing, a very proper gas exchange, superior cylinder filling, a very high EGR tolerance, and a good combustion characteristics for a rather late retarded combustion. For the advanced rapid heat-up measures and technologies, we can consider intake throttling, hot EGR, EGR bypass, internal EGR, exhaust VVT, thermal shielding of the components, and multi-post injections. And further on with the other technologies, I think you can read it by yourself. I don't have to guide you through the different aspects of these pillars here for the overall achievement of the targets. So coming furthermore to the overall machine efficiency. So if we have a closer look into the current situation, we have a quite surprising outcome where we can see that more or less the overall consumption split in the non-road mobile machinery is very much more or less covered by the heavier machinery. So more or less 78% of the overall fuel consumption in this NRMM sector is consumed by the big machines, and the small machines even having a large portion of the overall sold products and models is just below a quarter more or less. So for sure, which means for the below 56 kilowatt fuel consumption improvement is not a main priority, at least not a main driver. Here the cost for purchasing for the base product and maybe for the service and maintenance is much more dominating than the real world fuel consumption. The fuel consumption kicks in as the engine output increases. But as you have also seen before, we have the difference between the certification cycles and the real world all-day operational cycles. And here we identify different areas of load coverage in the engine map. And here we can see that maybe, for example, looking here at the upper left, middle left one wheel loader, where the main operating areas in over the entire speed band, but in low and mid load ranges for sure. Here, kind of hybridization, mild hybridization makes sense in order to reduce the real world fuel consumption behavior. If we go to a bulldozer application where the load profile concentrates on rated power, rated speed conditions, I think the clear way forward is to continue on combustion system optimization, and here upgrades in this regards provide a significant fuel consumption improvement. I think it is always worth to look into other applications. So here, for example, you see FEV's line walk in terms of efficiency improvement for light-duty on-road applications, which are going continuously upwards. Actually, we have to say, unfortunately, not driven by European developments, more driven by Asian developments, because in Europe we have stopped this part of the story. So here we see massive from Chinese, Japanese manufacturers going into higher efficiencies. And if we compare this on the right side in the scatter band, some typical non-road mobile machinery in the 2.5 liter class segment, and we see the gap towards the latest announcements coming from the light-duty side, I would say there's a significant gap between what is possible from the base engine side versus what is currently on the market. And I think here a good recommendation is at least to halven the gap in the comparison towards the on-highway applications. I think I pointed out that one major element of the future success in the non-road mobile machinery is a proper combustion system. And I think I pointed out as well that we need a quite high EGR tolerance, because we have to work with quite high EGR shares in the future in order to meet the ultra-strict emission requirements. We need variable shares of cooled and non-cooled EGR under several operational conditions. And in this context, I think the air supply is one of the key elements. And also here, I have to say, coming from a lot of experience from the on-highway applications, we have to have a closer look what is driving there the development forward for the last years. And I think here one element is found in the so-called seat swell chamfer, which provides the opportunity to decouple the intake flow from the swirl generation due to some eccentric chamfer at the fire deck of the cylinder head, which results, if we compare this on a one-to-one engine comparison, same compression ratio, same boost, same injection pressure. So we can see here that this kind of different air supply with a much better cylinder filling provides a significant improvement on the combustion process itself, resulting in better efficiency, resulting in higher EGR acceptance, resulting in an improved NOx particulate trade-off, because we run the engine typically with a higher air excess, which means normally then less soot and better fuel efficiency. The second aspect, which I think is also of high importance, is the improved coverage of production scattering. So you see here an example of more or less moving, shifting the valve position by plus minus 0.7 millimeters in all three dimensions, so X, Y, and Z axis, and you see that the swirl behavior more or less maintains as it is from the nominal status, which means the engines coming from the production line are very, very robust and identical, which means the calibration engineer at the end of the day can really go to the limits in the calibration, and he has not to consider a massive reserve and safety margins for some kind of production scattering. Okay. That's for the basic combustion system. Coming to the other topic, and I think here we see also coming from the on-highway installations, light duty as well as heavy duty installations, some increasing interest and tendency to go to kinds of hybridization. In some areas maybe more the mild hybridization, in other areas more the strong hybridization, even going up to serial hybrids. Here one example for a construction equipment machine where we replace the original 75 kilowatt engine by a smaller one, inline 3 with 55 kilowatt, and adding an E-system towards the overall application. And this resulted in one cycle in the main cycle in up to minus 10% fuel consumption improvement, plus adding further functional benefits in the operational profile towards the application. If we go into other details and have a closer look into the different speed and operational targets, we could even identify an improvement up to 33% in the typical V-cycle of the conventional wheel loader. But it is always a portion which consists on the improvement on the hardware in conjunction with the proper operational strategy in order to maximize the benefits of the usage. Then stepping over towards the carbon neutrality finally, I think we have heard this also in some of the speeches before. We have to go to change the fuel, get rid of the fossil elements, and here we have just in principle an overview about the conversion towards hydrogen operation, so typical development steps starting with system design, going over the system optimization, prototype testing, and then coming into the concept demo and the proof of concept for the generation 1 conversion, in this case of the 2.5 liter engine, which we executed, for example, for different companies in the recent past. The main areas which we have to touch in a successful conversion from a typical diesel engine towards hydrogen operation are summarized here. So we have to redesign the cylinder head, we have to work on valve timing and air supply, trim the charging system, include an adjusted intake manifold with a more sophisticated, more precise throttle control, implement the medium pressure hydrogen DI injectors, adapt the fuel injection and combustion strategy, the piston design, the conrod design, and also have some look on the piston liner compound, as we have the risk of accumulation of hydrogen in the bottom end of the engine in the crankcase, which can cause for sure some issues in longer operation. Main areas where we have to work on is in order to avoid abnormal combustion and pre-ignition is found for sure in the piston design, in the charge motion, where normally the diesel engine with a swirl supported combustion principle is not the optimal starting point, so we have to work on the improvement of bringing in tumble motion towards the combustion system in order to mitigate this abnormal combustion effects and pre-ignition events. Sometimes we have to work on the valve if we want to go to higher load and higher efficiency levels, have to avoid the hot spot coming from the valve situation. in order to suppress the abnormal combustion events. This can be also for sure be supported by numerical simulations, introducing different methodologies, trying to homogenize the mixture formation in the combustion process by more pronounced charge motion and kind of spray guiding. And this results then typically, as we also have seen in the previous speech, to a quite excellent emission behavior where we have real low engine out or tailpipe emissions, comparing the base diesel engine here with a converted hydrogen engine. So it gives us a very good status. Nevertheless, from a FEV perspective, we would summarize that we would need for some kind of, I would call it social requirement, we would need some kind of SCR system on board of the application, and we would also recommend to put a kind of particulate filter, maybe an open or a gasoline type particulate filter, in order to be protected against any kind of public concern with regard to particulate emissions, even while meeting the legal targets, just to avoid stress coming from the public side, and also to be prepared for a discussion maybe 5 or 10 years after introduction of the model. I think this is a learning out of the recent past, that the interpretation of regulations as we did it 10 years ago may not maintain the ongoing years. So, coming finally to my summary and conclusion. So, I think within my speech under the headline Squaring the Circle, I first described you the upcoming challenges for the non-road mobile application. Emission reduction is on one hand for sure a driver for technology improvement and upgrading, besides the fact of carbon neutrality, going either mostly hydrogen, for sure also ammonia, but this is maybe more for the marine and larger engine applications. Then I think I pointed out that we see a major contribution from an optimized combustion system in order to meet the ultra-low emission requirements in the future, while simultaneously improving the fuel efficiency of the application. The US Tier 5 final standards can be met by a proper matching of the engine out emissions by the combustion system with a carefully designed exhaust after treatment system, and for sure hybridization can support robust and long-lasting emission compliance, especially if you consider also the extended full useful lifetime settings. And hydrocarbon, as mentioned before, represents also for us the main route for defossilization on the non-road mobile machinery sector. The PFI solutions depict the cost-attractive, fast-to-market solution. Mid- and long-term aspects are going towards the DI combustion principle, going to higher performance density and higher efficiencies. Knocking and abnormal combustion events describe key challenges for the hydrocarbon conversions, and in-cylinder charge motion is for us one key aspect in order to do some principal improvement on this tendency of pre-ignition, knocking, and abnormal combustion, because this is working on the main source. I'd like to thank you for your audience, and I'm available only today for some questions, either directly or later during the break. Thank you very much.
Thanks, Thomas, for that very nice, detailed technical presentation. A little bit of a step change from the others, but quite important in this first session to cover every base. Quick question for me. SCR under 55 kilowatts, do you see any need 37 to 55 for SCR in Tier 5 potentially or not?
Hopefully not.
Hopefully not. I think that's
sorry for the catalyst providers, but I think for the OEMs, we know the very tight packaging for the small machinery, and unfortunately maybe the OEMs would require smaller diameters, but the offers are maybe more in the standard categories, which makes it rather short but wide, which is not good for preparation and good efficiency, so therefore hopefully not.
I think fortunately that in Tier 5 in California, below 130 is preempted anyway, so they might not. I think they're hoping not to, but in the future, who knows. Any questions on the floor before we move on to me? Yeah, Alan Tolley, JCB.
Thanks, Thomas. Very interesting presentation. A question following up from the one previously on hybrids. You mentioned hybrids here for efficiency improvement. Do you see an opportunity for hybridization or electrified engines for emissions control? I'm thinking thermal management, transients, etc., thereby simplifying possibly the after-treatment system.
Yes, we see it, and I would say I think the non-road mobile machinery is often following the on-highway applications, light duty and heavy duty in a certain way. And we see this tendency at the moment regarding hybridization coming from the on-highway business, which is also preparing then the ground maybe for some cost-effective hybrid solutions, which can be taken over then by the NRMM sector. Yeah, so yes, absolute, we see this in different shades. Mild hybridization, 48 volt, rather simple systems for the more cost challenging applications, and maybe more powerful, more sophisticated solutions for the bigger machinery. Yes, absolutely. And also with regard to the extended full useful lifetime, where the hybridization or the electrical part can compensate a deterioration of the exhaust after treatment as function of time, or also if the control of the airflow, the HFM is getting a little bit aged and drifting, and all these aspects. And you might remember my chart where I said we go to 10 milligram per kilowatt hour, because we have on one hand we have the production scattering, on the other hand we have the aging effects, and especially for the aging effects, I think the electrical system can be a kind of compensator. Yeah.
Yeah, thanks.
Thanks, Alan. Any more on the floor? No.
Thank you. Jakob Pfeiffer from DNX. So thank you very much for the interesting presentation. One question, you showed the 10% fuel consumption decrease by hybridization, and you mentioned you are going from a 75 kilowatt to a 55 kilowatt engine. The question now, I didn't look for that now, but from regulatory side on the emissions, for example, if you go for the combustion engine from 75 to 55, does it also change automatically in the regulation, or does the regulation says, okay, we are always looking on the combination and on the end power level of the engine, even if it's hybrid?
So many thanks for the very interesting question. The project I referred to was a demonstrator project, and it was under the boundary conditions that the application maintains in the above 56 kilowatt class. So even with the 55 kilowatt small engine, all the regulations and the engineering tasks were set according to the above 56 kilowatt status. Yeah.
But I think, if I'm right, it's from an emissions point of view, you go down to 55, allows you to remove the SCR.
This was not going in direction of Tier 5 final, so it was according to an in-series emission regulation, stage 5, and therefore we maintained the existing emission concept.
I think just to finish off, in the Netherlands has done a lot of work on that, and they call it bin hopping. And all the TRUs, the transport refrigeration units, were 19 kilowatts. They moved them to 18 to avoid emissions, and now they're up in arms. So we can talk about that. But then thanks so much, Thomas, for your presentation.